All right, hey guys, what's going on? So again, we're starting to look, you're starting to look at me before we look at the iPad, just because I want to go over the brief of what we're going to cover in this video, and then we're going to dive into the mathematics. So today we are going over, again, Statistical Mechanics by Leonard Susskind. His videos, again, are pretty long, roughly 2 hours long each, and I have decided to condense his material into this playlist. Now, today we're going to be going over the partition function. We went over probabilities, we went over entropy, we went over how we can calculate numbers of states of a system pretty slowly, right? We have sort of been gradually getting to this point where we can start talking about the partition function. The partition function is very, very important. And the reason it's very important is because we will be able to, probably not in this playlist, but we will be able to understand the partition function in the context of quantum field theory. And it's going to be very, very important for us to understand that. And that's just a little taste at what the partition function is very good at doing. The partition function is also one of the most essential topics or things to understand in statistical mechanics, because if you know the partition function, then you can calculate almost anything you want within statistical mechanics. That is how powerful this thing is. So without further ado, let's get right into this material. All right, so when we're talking about the partition function, the first thing we want to go over is just some review of what we've gone over so far. So to start our summary, we went over law of probabilities. Oh my gosh, I'm erasing. Let's undo that. We went over the law of probabilities, right? This is the statement that all probabilities must equal 1. Then we went over assigning some value to each state that has a probability within a system, right? So you have some energy of some particular state, and you can calculate the average energy given a set number of states. And that's this guy right here. Then we calculated the number of states in terms of the probabilities of each state that we could have. And that was given by this guy right here. So the log of the number of states was equal to the sum of the probabilities times the log of each probability. Then we calculated the same thing essentially, right? This is the occupation number, O. This is the number of states given some value n, right? This n here. What is this n? This n is the total number of states, right? So you have state 1. So n can be calculated by p1, or by n1 divided by p1, right? If you just manipulate this equation. But n here is the same as these n's right here. And the sum of all of the states, the number of states is essentially what n is, right? That's given here. So we have all these relationships that we went over. Right, now let's get into the real fun of statistical mechanics. And this is calculating the partition function. And what Leonard Susskind does is he says, look, the partition function is a product of an attempt to minimize something given some constraints. So we start off, so the two constraints that he says, we are looking at the probability, all the probabilities of a state or of a system, all the probabilities that are associated with each state in that system have to equal 1, okay? Okay, that implies this, right? You just bring 1 over and you get 0. Okay, that's all fine and good. And then we take this constraint. This is our second constraint, right? So the sum of the probabilities times the energy of each gives us our average energy. Subtract the average energy over on both sides, we get this, right? So these are, I think, are pretty easy to understand. Now, let's talk about Lagrange multipliers, right? Because this is how Leonard Susskind goes about this. He says, okay, this is what we have for our entropy, or the number of states in our system, okay? And he says, we want to minimize this, okay? the way we're going to minimize this is we're going to say, well, okay, I'm just going to take negative s really quick, and I'm going to call, so negative s is just the negative of this, right? So that's this. But then we have this prime here. So this prime is, we're defining this to be a new variable. S prime is different than s, okay? S prime is the entropy, the original entropy of the system, plus 0, right? This is 0, right? Because this is 0, plus 0, right? So you might think this is kind of weird, but these are the constraints we're putting into the system, okay? And then we have a weight on the system. So we're not changing this guy, but we're putting constraints into this guy, but we're still not changing it. So this is a little bit of a mathematical manipulation, if you will. And then we're adding weights to these guys, and we want to understand what these weights are, and these are going to be important. So where are the weights? Well, we want to take the derivative of this new variable. So we can take the derivative of this, take the derivative of this, and take the derivative of this. And when we do that, we're taking derivative of this, which is this, right? This is just chain rule, or product rule, right? This times this, so this is going to be the product rule. And then the derivative of this guy, right? Well, this here, if we're taking a derivative with respect to pi, well, this is just going to be this constant right here, right? And then there's no pi here, so that's just going to be 0. Same thing here, right? So the derivative with respect to pi is just going to be this, because there's no pi here. That's good. So that's going to go to 0, and we have our beta ei. Okay. So far, so good. Now, to get from here to here, so if we say the log of, so this here is 1, right? The derivative of pi with respect to pi is just 1, so that's here. Then we have pi times the derivative of pi, derivative of log pi with respect to pi, right? Well, that's 1 over pi if we remember something from calculus. That's something just from calculus, right? So then this is going to cancel out. And then these guys just get carried over. This guy gets canceled out to 1, right? So we have this 1 here, and this guy right here. So if we set the derivative now of this new variable to 0, we've essentially found a minimum, right? We found a minimum. So this is the statement that we find a minimum. Or finding a critical point, if you will. Let's call it a critical point. We're finding a critical point of S prime, given the constraints. Okay? So now, if that's all equal to 0, well, we just bring this over, right? We bring this over here, and just through taking negatives, right? So we're not really bringing this one over, we're more bringing these guys over, right? So 1 plus I, bring that over, has to be a negative. Bring this guy over, has to be negative also, right? So this here is the relationship. And then we have this right here. So how do we get from this to this? Right, so from this to this, we're just taking the exponential. Okay, and then this guy here, we're going to call 1 over z, right? So this here, we're going to call 1 over z. And z, as you know now, or as you sort of anticipating, is the partition function. Right, that is the partition function. This is the important thing. So what does this tell us? This tells us that 1 over z times this is going to give us the probability of some ith state. Okay. Take a look at that for a second. Let it sink in. You could pause the video. Now, we want to apply these constraints to see, we've applied the constraints to the thing that we want to minimize. Now we can take a look at our constraints again, because we want to make sure these constraints hold true, not just for the minimization of this new variable, but we also want to make sure that they hold true for the partition function as well. So if we apply the constraints again, so here's pi, right? So this is pi. That means this all has to equal 1. Okay? This means that if we multiply both sides by z, well, we get this. Okay, let's keep that in the back of our mind. We say, okay, this guy, so applying the second constraint. So this comes from the first constraint, right? Because the sum of the probabilities equals 1. Applying the second constraint, okay, well, this is the probability that we've set up here, times EI equals the average of E. Okay, we can keep that one in mind too. Now, if Z equals this, which is what we said right here, the derivative of Z with respect to beta, well, that is just going to take this constant out and bring it here, and the negative. Okay. And then we say that if we multiply by 1 over Z, multiply by 1 over Z on both sides, well, this here, again, as I've highlighted in green, is just pi. Right? So if that's pi times EI, well, that's just the average of E. A lot of this is just really mathematical manipulations. And we get that the average of E, the average energy, is equal to the derivative of the partition function with respect to beta times 1 over the partition function. That's kind of interesting, right? So we can calculate the average energy, right, in this way right here. Calculate it like that. But now we can calculate it like this also. So up here we have the average energy in terms of the probabilities. Here we have the average energy in terms of the partition function. Something a little bit more general. If we don't know the probabilities, right? If we don't know the probabilities of each associated state, well, perhaps we know the partition function, and that can help us. Okay. So there's another interesting relationship here that Leonard Susskind goes into just a little bit. I think he could go over it a little bit. He kind of brushes over it though, right? So he says E beta EI, right? So again, this guy, well, over here, if we take the log of Z, and so what does taking the log do? Well, that takes our exponents and brings it over here, and we have the log of the sum over I of E. Well, there's no I in E, right? So that's just going to be 1 because the log of E is 1. And we can bring the summation out because, again, we're summing over I. So if we sum over I, this is what it looks like. Now, if we take the derivative of this with respect to beta, that's just going to give us this constant. The sum of I over EI, well, that's just the total energy, right? So the total energy is equal to the derivative of the log of Z with respect to beta. And these are two important equations that involve understanding the energy of a system in terms of the derivative of some partition function. And that's why the partition function is so important. So if you like this kind of content, again, you can hit that subscribe, hit that like button, and I will see you guys in the next one. Bye.